Greetings, Professor. I'm Satish Kumar Armugam. Today, I will present about our project on structural and finite element analysis of a rocker arm. Thank you for the wonderful opportunity given for us to present our project. Our group members are Austin, Tarun, and myself, Satish. I'll begin with introduction and walk you through constraints, design parameters, objectives, and materials. Introduction. A rocker arm is a critical component used in high-performance suspension system, which transfers load wheel through push rod and then into the damper. In this project, we use ANSYS Workbench to perform detailed static structural and finite element analysis. This study integrates geometric assessment, meshing, sensitivity analysis, and optimization to ensure structurally reliable rocker arm. From the image, you can see that the rocker arm is connected to the chassis at the center, push rod to the left, and damper to the right. The main objective of this project is to perform static structural analysis and conduct sensitivity analysis on at least two design parameters like arm gap width, fillet radius, and rib thickness. And finally, optimization is performed to minimize deformation while maintaining safe stress level. The image shows the rocker arm. Design variables includes arm gap width, which is marked as 1, fillet radius close to the loading area, which is marked as 2, rib thickness, which connects the arm, marked as 3. We have 4 ribs. The design constraints is to maintain 1 measure stress less than 300 megapascal and reduce deformation less than or equal to 0.3 mm while maintaining factor of safety greater than or equal to 1.5. We had chosen aluminum alloy 7075T6 as our material because of its high strength to weight ratio, fatigue resistance, and proven motorsport usage. The properties are Young's modulus of 71 gigapascal, shear modulus of 26.9 gigapascal, and Poisson ratio of 0.33. Alternative materials used for rocker arm is steel alloys, titanium alloys, and magnesium alloys. From here, Austin will take on.
To simulate the forces acting on the rocker arm, we applied the following conditions. A fixed support was applied at the inner diameter of the fixture hole as shown by point A. This restrained all translation and rotational movement. In normal operation, the rocker arm experiences forces from bumps and the weight of the vehicle from the push rod and reactionary forces of the damper. 1,500 Newton load in the positive Y direction was applied at the push rod hole B, and 1,250 Newton load in the negative X direction was applied at the damper hole C. Both loads were applied as bearing loads in ANSYS to ensure distribution around the surfaces of the hole. The part is symmetrical across the XY plane, so a half 3D model was used to simulate the part. The full model was cut at the XY plane and symmetry boundary conditions were applied at sections highlighted in red. To begin the meshing process, we started with an initial mesh using the tetrahedron method with an overall mesh size of 2 millimeters. The results from it showed that it was now converged. The average and unaveraged stress results were different and located at different areas of the part, showing up at internal radii near the loads and constraints. We then ran the simulation with finer overall meshes from 2 millimeters to 0.5 millimeter element sizes with a step size of 0.25 millimeters. During the process, we found that the initial geometry had sharp edges where max stresses were located and caused there to be singularities. To avoid this, we slightly altered the geometry by increasing the chamfer to not interfere with the edge of the fillet radius. Looking at the results from the process, we chose to use a general mesh size of 1 millimeters. Less than 1 millimeters, the stresses started to increase. We then applied a refinement at the internal fillet radii of the part, which was where the stresses were mostly concentrated. Nick. This is the result, the total deformation result of the final mesh. We found that it had a maximum deformation of 0.39873 millimeters. For the stress results, we found that the maximum stress was 201.91 megapascals, and some image, and these are some screenshots to show where the stresses were higher than the rest of the part. And Tarun will go over the sensitivity and optimization processes.
Now, moving on to the sensitivity analysis, which forms the major part of our design improvement process. In this project, the goal of the sensitivity analysis was to understand how different geometric parameters influence the performance of the rocker arm, particularly maximum deformation and equivalent von Mises stresses. And the first step in this process was to parameterize. So in Design Modeler, we expose two major design variables. One is fillet radius and the other is arm gap width. Next, we designed the responses that we wanted, that is the maximum von Mises and the maximum total deformation. So once these responses were defined, we then generated the design points using design of experiments approach. So in DOE, systematically varies the parameters within the chosen region, and this ensures we explore the design space efficiently instead of testing parameters randomly. Finally, we all the design points were solved. We performed post-processing, which we compared influence of fillet radius and the arm gap width of the rocker's structural performance. Next slide. So these are the design points of the design of experiments where the fillet diameter was varied between 5 mm and 7 mm, and the arm gap width was varied between 8 mm and 10 mm. So a total of several design points were created and solved, giving us a clear understanding of how these two parameters influence deformation, stress, and the mass. Next slide.
I would like to add one point. The rib thickness, change of rib thickness doesn't show any improvement. So we had only gone with the fillet diameter and the arm gap width.
Yeah. So these are the 2D plots of the deformation, and the arm gap width and the fillet radius shows like how it influences the deformation of the rocker arm. Next slide. And these are for 2D plots of the equivalences where the arm gap width and the fillet radius shows how it influences the equivalences results. So here we see the combined response surface generated by ANSYS. So 3D plots help us visualize the relationship between parameters and the outputs. So first is the total deformation response. It clearly slopes downwards as the arm gap width decreases, confirming the stiffness improvement. And next is the equivalent stress response, where the fillet radius decreases, showing it reduces the stress concentration. And also we have added the mass surface, so it shows slightly increasing both the smaller fillet and the smaller gap width, which is expected. So these surfaces help us identify combination of both parameters where deformation and stress meets the constraints. Next slide. And these are the optimization targets where that is going to be used. That is, the maximum deformation is less than 0.3 mm, and the maximum stress is less than or equal to 150 megapascal. So these targets ensure the rocker operates safely and maintains motion accuracy. And this chosen point represents the best combination of parameters that meets the target. So we have gone with the chosen point of 8.0005 mm. So this slide shows the deformation results of the optimized geometry. So the maximum deformation reduced from 0.3982 mm to 0.290 mm, and this significant improve the performance, especially for suspension component where precision is critical. Next slide. So these are the optimized bond stress results where the maximum stress was 201.91, and after optimization, the maximum stress reduced to 135.94 megapascal, well above the allowable limit of 150 megapascal. This gives us a strong safe factor of safety while maintaining the mass and manufacturability requirements. So this project successfully demonstrates the entire workflow of finite element analysis applied to the mechanical suspension component. First, we perform geometrical evaluation and meshing, ensuring high quality quadratic tetrahedral mesh was used. Next, we analyze the rock under realistic push rod and damper loading conditions, where the combination of bearing load, symmetry constraints, and the refined local elements. And also, we observed higher deformation and stress before the initial condition. And through systematic sensitivity analysis, we identified fillet radius and arm gap width was a key variable, and then we arrived at the best performing optimal values. So it reduced the deformation to 0.29 mm and the stress to 135 megapascal, achieving better load distribution. And overall, this work highlights the importance of combining FEA with optimization techniques to achieve stronger, safer, and more efficient mechanical design. Thank you.
Thank you.